Hi everyone, welcome back to Physics 11. So far in this unit we started talking about energy, work, and power. So whenever you have a process, whenever you have some energy transfer from one type of energy or transformation from one type of energy to another, I mentioned that you're always going to lose some of the energy to heat. So you're going to lose during that conversion, uh, and by lose I mean it's going to get transformed into heat, which is not useful to us. So that's where efficiency comes in. So how efficient is each energy transfer? So in this case, in this first slide, we have three examples of different light bulbs. So the first one is what's known as incandescent light bulb, which basically has a tungsten filament inside of it. And as you run the current through it, it heats up and it glows, producing light. Now this one produces a lot of heat as well. So to us, the useful energy would be the energy of light, not the heat energy. So the heat is basically wasted energy that we don't care about. Then in the middle, we have a fluorescent light bulb. So this one works by having an inert gas inside of it. And then it has this coating on inside of this glass tube, which then as the gas gets ionized, so it has higher energy because of the electricity that you run through it, it basically hits the particles on the coating and then it makes the coating glow, producing light. So the fluorescent light bulb is a lot more efficient compared to the incandescent light bulb. That's why, for example, most schools have fluorescent light bulbs. That they have longer tubes rather than just these bulbs. And on the right side, we have the kind of fairly recent type of light bulb, which is the LED light bulb. Now, LED itself has been around, so the light emitting diode has been around since the beginning of the 20th century, and it's been mass produced since the 60s. So it's been around for at least 70 years as a mass produced um, item, but it's only recently that's technology has advanced enough to actually make light bulbs, to make LEDs efficient enough to make light bulbs and headlights for cars and stuff like that. So, for example, if you look at the rating on the light bulbs, for example, let's say this one is 60 watt. So it will say on it 60 watt, which means that this light bulb consumes 60 watts of energy. So that means 60 joules every second. And then on this one might say something like 13 watt, which means that this one, it might also say equivalent to 60-watt light bulb, which means that it will produce the same amount of light energy compared to the 60-watt incandescent light bulb, but the transfer from electrical energy to light energy is a lot more efficient. So you actually use less, you waste less energy to heat. So it only takes 13 joules of energy to produce the same amount of light as it would with 60 joules of energy per second in the incandescent light bulb. And then the LED light bulb, let's say maybe a little more efficient than the fluorescent. So let's say maybe it's 12 watt, which means that this will use 12 joules of energy every second to produce the same amount of light as the 60 watt incandescent light bulb or the 13 watt fluorescent light bulb. So the efficiency between the last two is fairly similar, although some might be more efficient than the fluorescent light bulbs. But I think the advantage of the LEDs is that it's supposed to be much more long lasting compared to the fluorescent light bulbs. So they have much longer lifespan. So that's why if you go to stores today, you're probably not going to find a lot of, definitely you're not going to find any incandescent light bulbs anymore. You're either going to find either fluorescent or LED light bulbs. So let's see what else can we say about efficiency. So efficiency is a measure of how much energy is wasted by a machine. That doesn't have to be a machine, could be any process, right? It's just a matter of transferring energy. So if you want to be more general, you can say how much energy is wasted by or through an energy conversion. So you're converting one type of energy into another. But normally we do use machines, and you can actually, I guess, count a light bulb as a machine. So again, machines are useful because they allow us to use less force over a longer distance to the same work. Because remember, work is force times distance, and you can get the same work done if you have less force but more distance, or more force and shorter distance. So this comes down to mechanical advantage. So we have some primitive tools that you probably remember from your junior science class. We have inclined plane, wedge, a lever, wheel and axle, screw, and a pulley. All of these are primitive machines that we use, that people use for centuries now, if not millennia, to help them do a lot of the work. For example, the inclined plane is very simple, and the way this works, for example, if you had to push a heavy object or bring it to some height, let's say the height that would go from the ground to here, if you just lift it straight up, it might be too heavy to do. But if you apply a smaller force over a longer distance, which would be like, let's say, pushing it or pulling over this incline, which is the hypotenuse of this triangle, this is longer than the opposite side. So you apply smaller force over a longer distance as opposed to applying a bigger force over a shorter distance to lift it. So that's an example of, again, using less force over a longer distance to do the same amount of work. So what else can we say about efficiency? Well, let's take a look at, again, at the second law of thermodynamics, which states that whenever there is a energy conversion, some of the energy will be lost to a form of heat, which is basically not useful to the process that you're trying to achieve. You're gonna see more of second law and first law of thermodynamics in your chem class if you take chemistry, and definitely in more later on in physics class. So in kind of simpler terms, second law of thermodynamics states that whenever work is done, some energy is converted to heat. So you have to remember that for physics 11. So whenever you transfer or transform energy from one type to another, some of it will be lost to heat. Which means that whatever the work that you put in, so whatever the energy amount that you put in, let's say if it's electric energy and you have a motor, electric motor, the work they get out from that motor as mechanical energy is going to be always less compared to the work that you put in. Okay, or the power that you put in is going to be greater than the power that you get out. So again, some of the energy that you put in will be lost to friction, which in turn will produce heat. So again, the work in can be replaced with either energy in, and this can be energy out, or you can also replace this with power, because power is just energy per second, so you can also compare powers. So that's why we have the following. We have two equations. One of them, efficiency is defined as the work out over work in times 100%. So we're going to look at the ratio, and then we're going to convert the decimal to percent, where this number here, this letter here is called eta, Greek eta, which is the symbol for efficiency. Or we can look at the powers. So we can look at the ratio of power out over power in times 100%. So again, there are no units when it comes to efficiency. It's just a percentage, or sometimes expressed as a decimal. It's just a ratio. And again, the eta, the Greek letter eta, is used as a symbol for efficiency. Now, there's one other definition you might encounter. It's called the COP. So COP stands for the coefficient of performance, which is defined the other way around. It's defined as the, let's say, power in over the power out. And in this case, normally you're going to see ratios bigger than 1 or bigger than 100%. So do not get confused. Some of the ratings you might see on some of the appliances might say that efficiency is greater than 100%. Normally, it's not going to be the case, because always the work you put in is going to be bigger than the work out. So normally, this is always going to be less than 100%. Okay, so the only case that I can think of that you might get close to 100% if you're trying to get heat. Let's say you're trying to convert something into heat. So for example, a furnace could be nearly 100% efficient, maybe like 98% efficient, because if the only purpose is to create heat, that's one process that can be 100% efficient. But any other process, any other transfer of energy is always going to be less than 100%, unless you're talking about the COP, which is always going to be greater than 100%. You're always going to get like ratios over 1, whereas with efficiency, you're going to get ratios less than 1. So it's always going to be point something. Okay, so again, if you see something that says efficiency is greater than 1, they're not talking about efficiency, they're talking about the coefficient of performance. So let's take a look at one example which talks about efficiency. This one says an electric motor consumes 100 watts of electrical energy to obtain 90 watts of mechanical energy, or power in this case. Determine its efficiency. So we're talking about power here, we're talking about watts, so it's joules per second. So again, the efficiency is going to be the power that you get out over the power that you put in. So that's the amount of energy that the motor consumes, which is 100 watts times 100% here. So the power that we get out as a mechanical energy is going to be 90 watts of power over the 100 watts that you had to put in as electrical energy. So times 100%, we're going to get 90% as our efficiency. So in this case, our efficiency is 90%. So electrical motors are pretty efficient. Their efficiency is about 85 to 90, maybe 95% efficient, as opposed to internal combustion engines, which are theoretically at most, it can be, I think, 50, 60% efficient. In reality, they're actually much lower than that. In reality, most internal combustion engines may be like 35% efficient at most, at the crankshaft, not even at the wheels. At the wheels, let's say if we talk about cars, it's like 10% or 15%. So anyway, let's take a look at another example that talks about efficiency, and now we're going to look at a lever. So here we have an example. We have a lever that we're going to use to lift a 50 kilogram object. Let's say maybe it's a boulder in your backyard that you're trying to move. And you want to lift it by 10 centimeters. To do this, we must apply a force of 75 newtons to the other side of the lever, which will displace by 1 meter. So find the efficiency of this process. So the force that you're going to apply is going to be applied downward. So this is going to be our force applied. And this is the distance that you're going to apply it over. So you're going to apply this 75 newtons over 1 meter of distance. On the other side, because here we have to lift it up, so you had to do work against gravity, the force that we're concerned about is going to be our force of gravity, which is our m times g. And the distance we're going to lift this is going to be the 10 centimeters or 0.100 meters, which means that the efficiency for this is going to be defined in terms of work. So let's write it down. Let's write our efficiency equation as the work out over the work in times 100%. So again, our work out is going to be lifting the object, right? So that's going to be our force of gravity times distance 2. So Fg times d2, and then this is going to be our Fa times d1, and this times 100%. Now let's expand our Fg to m times g times d2, and this is our Fa times distance 1. So now we can plug in the values for the mass and the distances and the force applied. So let's do it down here. So the mass is 50 kilograms, so 50.0, so that's 3 sig figs, times the gravity, which is 9.8, times the distance. Distance 2 is going to be 10 centimeters, which is again 0.100 meters. And then the force applied is 75 newtons, so 75.0 times 1.00 meters. This times 100%. All right, so if you look at our variables here, this is 3 sig figs. All the variables that we plugged in there are 3 sig figs. 9.8 is a constant, so we're not going to count towards sig figs. So the final answer should have 3 significant figures. So 50 times 9.8 times 0.1 is 49. So we have 49. That would be 49.0. And then, of course, the bottom we're going to end up with just 75.0 down here times 100%. Now, normally you just do this in one step. You don't have to do it in 2 steps like I did here. So 49 divided by 75. 49 divided by 75 is 0.65. So we get 0.65333 repeating. So this would be 65.3%. So that's going to be our efficiency for this process of lifting this object of 50 kilogram. So there's this, I think there's a similar question in your practice question section. All right, so what else can we do with this? Let's take a look at one more example. So here's an example. It says, if a 3 horsepower electric motor has an efficiency of 85%, how long will it take for it to lift 60 kilogram object to a height of 10 meters? So in this case, what we have is horsepower as a unit. So horsepower is a unit of power, and it's a very old unit. It's been around probably for hundreds of years, if not thousands of years, because people have been using horses to do work for, since they domesticated the horse. So it's a universal unit, but again, it's not part of the metric system or the size system. So we do have a conversion that we had to do first. We had to convert the horsepower to watts. So 1 horsepower is 745.7 watts. So let's convert the 3 horsepower that we have here as our first step. So we're going to convert this to watts first by multiplying by this conversion factor. Now, we want to get rid of the horsepower, so the horsepower is going to go on the bottom, watts have to go on the top. So 1 horsepower is 745.7 watts. Now, this has 3 sig figs here, so our answer, once you convert it, should also have 3 sig figs. So 3 times 745.7 is going to be 2,237.1 watts. And again, I'm going to make a note here that this has 3 sig figs. So 3 sig figs. So I remember that when I use this number in my next calculation. Now let's write our equation for efficiency. So here's our efficiency, our power out, or our power in times 100%. So let's say we skip the 100% for now, we just drop the 100%. We'll deal with it later, or we can just convert this right now to 85% is just going to be 0.85. So this is our equation. Now, what is power out? What is power in? Whenever you see a rating on an appliance, that means that's the amount of energy that it uses. So that's going to be your power in. So this is going to be our power in. So the power in is given the 3 horsepower, and then we don't know the power out, but we can find it if we manipulate this equation to solve this for the power out. So in this case, all we have to do is to write the power out is going to be equal the power in times the efficiency. So the eta times the power in. So let's find the power out first by basically taking our 3 horsepower times the efficiency to get the power out. So let's plug in the values. And again, because we already converted the 85%, or you can do it here as a step, you can do 85% over 100% to convert it to decimal first if you want, or you can just plug in 0.85 times the power in, which is the number that we have up here. So 2,237.1 watts. Okay, and again, this has to be rounded to 3 sig figs there. So keep that in mind. And this has 2 sig figs. So really, we're going to end up with 2 sig figs in our answer here. So let's see what we get. So 0.85 times the 2,237.1, we get 1,901.5 watts. Now, the answer should be rounded to just 2 sig figs here because of the 85% efficiency, which is 2 sig figs. All right, so now we know power out. So what's next? We're still looking for how long. So this is asking us for the time, right? So how do we find the time for this? Now we know the power is work over time. So power is work over time. Now we're talking about the power out here, so we can add power out, which means that's the work out here that we would actually be looking at. But this allows us to find the time that we're looking for. So we know that work is force times distance, and this is over time. So that's what power is defined as. Because we're given a distance, okay, we are trying to lift an object, which means that the force that we're talking about here is going to be the force of gravity. So it's going to be our Fg, which we can calculate because we know the mass. So the only unknown then, we know the power out, the only unknown is going to be the time. So let's replace this and solve this for time and then plug in the values. So if you replace the t and the p out, basically, you get the equation for the time. So we get our Fg times the distance over the power out. We can expand this a little bit. M times gravity times change in height in this case because we're working against gravity. So we can write delta H here, or just H, final H, over the power out. So the mass is 60 kilograms, so 60.0, and then 9.8, and the change in height is going to be 10 meters, so 10.0. So we have 3 sig figs on the top. On the bottom, we're going to end up with 2 sig figs, but I'm going to use this whole number here in the calculation, 1901.5. And let's see what we get for the time. So 60 times 10 times 9.8. Let's see, what do we get? 60 times 9.8 times 10. We get 5,880. And then we're going to divide it by 1901.5. We get 3.0. So I'm going to round this to 3.1 rather seconds. So 2 sig figs because again I know that this has 2 sig figs there. So that's going to be our time that will take for this motor to lift this object 10 meters from whatever height it was before. So here's another way you can use efficiency to solve a question using power and work definitions to find, in this case, the time that it takes for this process to happen. Okay, so there's a couple of questions that you have. I think there's 4 or 3 questions in the practice section, and I think some of them are similar to the examples I did here. So make sure you complete those, and if you have any questions, make sure you post them as a reply on Teams.